the auto-ionization of water, and the concept of pH. If a water molecule acts as an acid by losing a proton, then what would be the conjugate base that forms? And of course it would be the hydroxide ion. If a water molecule acts as a base by gaining a proton, then what would be the conjugate acid that forms? And of course that would be the hydronium ion H3O+. Now write the reaction of two water molecules reacting with each other, where one acts as an acid and the other a base. And you should have written H2O plus H2O yields H3O plus OH minus, and it's an equilibrium situation. Now, write the mass action equation for water ionizing if H2O is considered a pure liquid with a constant concentration, so that the equilibrium constant can be expressed as Kw. What would it look like? What would the mass action equation look like? And of course, water molecules would not appear in the mass action equation, and it would simply be Kw equals the concentration of hydronium ion times the concentration of hydroxide ion. So if Kw equals 1.0 times 10 to the minus 14, and it does at 25 degrees Celsius, what would be the hydroxide ion concentration if the hydronium ion concentration is 5.4 times 10 to the minus 8? Calculate it and come back and check your answer. So you'd solve it this way, and the hydroxide ion concentration would be 1.9 times 10 to the minus 7 molar. In a neutral solution, neither acidic nor basic, the hydronium ion concentration equals the hydroxide ion concentration. That's a neutral solution. So given that Kw is 1.0 times 10 to the minus 14, what is the value of both hydronium and hydroxide ions in a neutral solution? And here's a hint. Let X equal the concentration of hydronium ion and the concentration of hydroxide ion. Try it, come back, check your answer. So Kw equals this. 1.0 times 10 to the minus 14 equals x squared, because H3O plus is x and hydroxide is x. Therefore, taking the square root, we get the concentrations in a neutral solution of hydronium and hydroxide ions are both 1.0 times 10 to the minus 7. pH is defined as the negative logarithm of the hydronium ion concentration, and pOH as the negative logarithm of the hydroxide ion concentration. So what's a logarithm? Imagine our 10 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now it's possible to represent each one of these numbers as an exponent of the number 10. For example, 10 to the 0, everyone knows is 1. And 10 to the 1, everyone knows is 10. So any of these numbers in between can be represented as an exponent of the number 10 as follows. 2, for example, is 10 to the 0.301. 3 is 10 to the 0.477. These are logarithms, or logs, these exponents of the number 10. But what good are they? Well, for example, suppose we're going to multiply 10 squared by 10 to the 4th power. That would be akin to taking 10 squared, which is 10 times 10, and multiplying it by 10 times 10 times 10 times 10. And when we do that, we get 10 to the 6th power. In other words, we've done a multiplication here by adding the exponents of the number 10. 2 and 4 is 6, 10 to the 6th. So we've replaced multiplying with adding. For example, if we wanted to multiply 2 times 3, we could do it this way with logarithms. 2 is 10 to the 0.301. and 3 is 10 to the 0.477. We multiply these two numbers and we get 10 to the 0.778 by adding the exponents. And when we find the value of 10 to the 0.778, guess what it equals? Of course it equals the number 6. So we've taken 2 times 3, converted them into logarithms of 10, and added them, and then converted that exponent of 10 into the actual number. So if the hydrogen ion concentration is 1 times 10 to the minus 5, for example, that's 0.00001 molar. The pH is simply 5. Or in a neutral solution, the pH equals 7, where the hydronium and hydroxide ion concentrations equal 1 times 10 to the minus 7. It's just that pH is an easier way to grasp the acidity or basicity of a solution. Here's your pH scale ranging from 0 to 14. From 0 to 7, it's acidic. From 8 to 14, it's basic. And if it's right at 7.0, it's a neutral solution. So we know that hydronium ion concentration and hydroxide ion concentrations multiplied together give a constant 1 times 10 to the minus 14. Therefore, pH, which after all is a logarithm, the negative of a logarithm, the pH is a logarithm plus pOH, which is another logarithm. We are multiplying terms by adding their logs, and it comes out to be 14. The log of 1 times 10 to the minus 14 is minus 14. The negative of that number is 14. So pH plus pOH equals 14. The normal range of pH is 0 to 14. pH of 0 has a hydrogen ion concentration or hydronium ion concentration of 1 molar. When the pH is 14, the hydroxide ion concentration equals 1 molar. But pH can be negative for very acidic solutions, less than 0, or pH can be larger than 14 if you have a very alkaline solution. So let's practice converting a hydronium ion concentration, in this case 3.64 times 10 to the minus 4, to pH. Take your calculator and follow along. First enter 3.64 times 10 to the minus 4 into your calculator. Then find the LOG button, not the LN button, and press it. And you should see minus 3.44. You're going to change the sign because pH, after all, is the negative of the logarithm. Change the sign to 3.44, and there's your pH. Now, going in the opposite direction from the pH to the hydronium ion concentration, first enter 8.58 and push the plus minus key to make it minus 8.58 in your calculator window. You must negate it because, after all, pH is the negative of a logarithm. Then hit the 10 to the x key. Sometimes that's a second function key of logarithm, LOG. Some calculators use INV-LOG sequence. Each calculator is a little different on this score, so you have to practice and hunt around. And when you take the inverse log or the 10 to the x, your answer should be 2.57 times 10 to the minus 9. So here are 3 problems for you to try. Turn the playback off, try them, and come back, and we'll give you the answers and see if you've gotten it. Okay, here we go. The answer to the first one is B, 4.02. The answer to the second one is A, 9.98. And the answer to the third one is 5.4 times 10 to the minus 4. How did you do? Now, we're going to start talking about finding an equilibrium constant given equilibrium concentrations for aqueous solutions. This problem, the pH of a 0.21 molar solution of a weak acid equals 5.6, calculate the Ka. So what we want you to do is write the reaction, write the equilibrium expression, and use the IRE setup. That's initial, reacts, and equilibrium, much like you did in the chapter on equilibrium, to solve the problem. Turn the playback off, try it, and come back and we'll see what the answer is. So if you do this, the pH is 5.6 at equilibrium, and that means hydronium ion concentration equals 2.5 times 10 to the minus 6. It also means that the conjugate base, A minus, is 2.5 times 10 to the minus 6. So we can fill out the IRE table as follows. Here's our reaction. Initially, we have 0.21 molar of the HA, 0 of hydronium, and 0 of A minus. And we know that the hydronium ion concentration is 2.5 times 10 to the minus 6 at equilibrium, and so it is with A minus. Well, where did these come from? They had to have come from HA ionizing. Therefore, the amount of HA that reacts is minus 2.5 times 10 to the minus 6. So at equilibrium, we have 2.5 times 10 to the minus 6 molar of hydronium ion, the same amount for the conjugate base, A minus, and for the starting material, HA, we have 0.21 minus 0.25 times 10 to the minus 6 of it that's going to ionize. Now, this is a very small number, 2.5 times 10 to the minus 6. It's what? 0.00000025. That's really small. And if we subtract that from 0.21, what do we get? Just about 0.21. So that's why we're going to use this approximation to simplify the problem. So we take our mass action equation, we plug these values into the mass action equation, we solve for Ka, and we get 3.0 times 10 to the minus 11. Now here's one for you to try. The pH of a 0.36 molar solution of weak acid HA equals 4.8. Calculate the Ka of the weak acid HA. So which one are you going to choose? Turn off the playback, try it, and then come back and we'll discuss it. Okay, the answer there is C, and we're going to show you why right now. So here's our problem, and the reasoning goes like this. If the pH is 4.8 at equilibrium, that means taking the negative antilog of 4.8, it means that the hydronium ion concentration is 1.58 times 10 to the minus 5. And it also means that the conjugate base A minus is also 1.58 times 10 to the minus 5. So we fill out the IRE as follows. Here's our reaction. Initially we have 0.36 molar of the HA. A quantity of it reacts, which we determined from the pH, to be 1.58 times 10 to the minus 5. We know this because the hydronium concentration was 1.58 times 10 to the minus 5, and that came from the HA ionizing. So the pH tells us how much of the HA ionized. And then at equilibrium, we have 0.36 minus 1.58 times 10 to the minus 5, which is, after all, a very small number, and we can ignore it and therefore use the approximate value, 0.36, the starting molarity, for the equilibrium concentration of HA. So take our mass action equation, plug in the values into our mass action equation, and we get 7.0 times 10 to the minus 10. Now in this problem, we're given the Ka. In the previous problem, we were calculating the Ka. Here we're given the Ka, and we need to calculate the pH of a 0.15 molar solution of HA. And we have to calculate the percent ionization, and if the X is negligible approximation, will that work or not? So what you're going to do is write the reaction, then write the equilibrium expression, use the IRE setup to solve it and calculate pH, hydronium ion, and A- of the solution. And then calculate the percent of ionization, which is simply the ratio of the HA that ionizes divided by the initial concentration of the weak acid. And finally, if the percent ionization is less than 5%, the X is negligible approximation will work. So here's our question. The Ka of a weak acid is 1.44 times 10 to the minus 6. Calculate the pH. So we set it up, we write the reaction out, and we write the IRE setup. Initially 0.15 molar of the HA. We say a quantity X reacts of the HA, forming hydronium ion and conjugate base A-. And at equilibrium, we have 0.15 minus X, which we're going to call just about equal to 0.15. And why can we do this? With the Ka being such a small number and the initial concentration of HA being relatively much larger, it would imply that this approximation would work and that X is negligible compared to 0.15. So now we can set up our mass action equation, solve it for X, and here's where we get rid of the quadratic. We just put in 0.15, the starting concentration, not 0.15 minus X. Set that equal to Ka, solve for X, which is 4.64 times 10 to the minus 4, and then calculate the pH from that, 3.33. Now, to calculate percent ionization, we take the concentration of the ionized acid and divide it by the initial acid concentration times 100%. And we get an answer of 0.31% ionized, that this weak acid is 0.31% ionized. The percent ionization also indicates if the X is negligible approximation can be used. If the percent ionization is 5% or greater, you cannot use the X is small approximation, and you must solve the problem using the mass solution such as the quadratic equation. Now, which one of these would require using the quadratic equation to solve for hydronium ion given the initial concentration and Ka? In other words, for each one of these, go through, calculate the concentration of hydronium ion, and do the test and see which one of these has an error that's too large to use the approximation. Okay, here we go. Let's test answer C first. And that's X times X divided by 0.082 is equal to the Ka of 1.8 times 10 to the minus 5. X is 1.1 times 10 to the minus 3. We do the test, and it's 1.35% error. It's okay to use. Now, what about D? Go through the same thing, plug in the values given in D. We come up with hydronium being 1.1 times 10 to the minus 2. Divide that by the initial concentration of 0.082 times 100%. And here we get 14%. So we cannot do the approximation with this problem. Now, we've just seen how weak acids react slightly with water to form a little hydronium ion and the salt of the weak acid, right? Well, it turns out weak bases react slightly with water to form some hydroxide ions and the conjugate acid of the base, just enough to make it a slightly basic solution. So ammonia, for example, reacts with water to form a little bit of ammonium ion plus hydroxide ion, enough to make it a basic solution. Or bicarbonate reacts with water to form carbonic acid and just a little bit of hydroxide ion. So for ammonia, here's our water molecule, here's ammonia, it's got that lone pair of electrons on the nitrogen, and what happens is the proton is captured by the lone pair of electrons on the ammonia to form the ammonium ion, NH4+, and the hydroxide ion, OH-. So some common weak bases and their Kb values. Here's carbonate reacting with water to form the conjugate acid bicarbonate and hydroxide ion. The Kb for that is 1.8 times 10 to the minus 4. Or ammonia plus water forms the ammonium ion and the hydroxide ion. Kb for that is 1.8 times 10 to the minus 5. Or pyridine and water forms the conjugate acid and a little bit of hydroxide. Kb for that is 1.7 times 10 to the minus 9. Or aniline plus water yields the conjugate acid and a little bit of hydroxide. Kb for that is 3.9 times 10 to the minus 10. So the question is, which one of these would produce the strongest basic solution? Which one is the strongest base? And if you look through all of these, the largest Kb value is the one that the reaction is going to go furthest to the product side, furthest to producing the most hydroxide, and therefore producing the strongest base. And that is going to be the carbonate ion. So answer B, sodium carbonate, is going to be the strongest base of these four. So here's a typical problem involving weak bases. Calculate the equilibrium constant for a weak base solution A minus, a 0.11 molar solution with a pH of 9.22. Essentially, this is done the same way as the weak acid system. The only thing you have to remember is that you're solving for hydroxide and not for hydronium ion. So here's our reaction. The weak base A minus reacts with water to form a little bit of hydroxide ion and the conjugate acid HA. The pH is 9.22 at equilibrium. Therefore, the POH, and we have to work with hydroxide because look at our equation. We're dealing with hydroxide here. So POH equals 14 minus 9.22 or 4.78. That's the POH. And therefore, if we take the negative antilog of 4.78, we get a hydroxide ion concentration of 1.66 times 10 to the minus 5, and it also means the conjugate acid HA is also 1.66 times 10 to the minus 5. So the IRE starts out like this, initially 0.11 molar of A minus, a quantity minus 1.66 times 10 to the minus 5 of the A minus reacts to form the hydroxide concentration and the weak acid concentration. And then at equilibrium, we have the starting 0.11 molar of the weak base minus 1.66 times 10 to the minus 5. And again, the amount that ionizes is very, very small, 1.66 times 10 to the minus 5 compared to 0.11. So we say that the amount that ionizes is negligible compared to the 0.11. And now we're able to set it up with the mass action equation and plug in the values to get a Kb of 2.5 times 10 to the minus 9. So now try this problem. Calculate the pH of a 0.23 molar solution of a weak base, B minus, with a Kb of 3.66 times 10 to the minus 6. And then calculate the percent ionization. So write the reaction first and write the equilibrium expression. Set up the IRE table and then use the mass action equation to calculate the hydroxide ion concentration and the conjugate acid HB concentration. Don't forget to convert the hydroxide ion concentration to pH. A lot of students forget that step. They just calculate POH, and the question is asking for pH. Then calculate the degree of ionization, which is simply the ratio of the weak base that reacts with water divided by the initial concentration of weak base. And if you multiply that by 100, you'll get the percent ionization. Turn off your playback, try it, then come back and we'll discuss it. So here we go. First, write the equilibrium expression out. That is, weak base plus water yields hydroxide and conjugate acid. Then set up your IRE. Initially, you've got 0.23 molar of the B minus and 0 of the hydroxide and conjugate acid. A quantity X reacts of the weak base to form X of hydroxide ion and X of conjugate acid. And at equilibrium, we have 0.23 minus X, which is just about going to be equal to 0.23. We can say X is negligible because the Kb is such a small number compared to the initial molarity of the weak base. So now we plug these into the mass action equation, and we get X times X divided by 0.23 equals the Kb, 3.66 times 10 to the minus 6. We solve for X, which is hydroxide ion concentration. It's 9.17 times 10 to the minus 4. And then we convert to pOH by taking the negative logarithm of the concentration of hydroxide to get a pOH of 3.04. But the question is asking for pH. Therefore, pH is 14 minus 3.04, or 10.96. Now let's calculate the percent ionization for this problem. The amount of the initial 0.23 molar B minus that ionizes is 9.17 times 10 to the minus 4. So the degree of ionization is the amount that ionizes divided by the initial amount, which comes out to be 3.99 times 10 to the minus 3. That's the degree of ionization. And if we multiply that by 100, we get the percent ionization, 0.399. That's the end of Chapter 16b. Next up, 16c, acid-base properties of ions and salts, polyprotic acids, and acid strength and molecular structure.